Okay, so Lecture 5, it will continue the discussions that we were having yesterday about the relations between computer science and philosophy when it comes to meeting the ontological needs of particularly scientists. But as I keep emphasizing, these needs arise wherever people have large amounts of data which they need to manage computers. So in the medical research world today, biomedical information is playing an increasingly important role in what is sometimes called high throughput experimentation, which means that one deals with thousands and thousands of samples, each one of which creates data which needs to be processed and exploited in order to give rise to results which will be of assistance in understanding human disease and in curing human disease. And there are many different kinds of data. These kinds of data have become available in the wake of the Human Genome Project. So there is genomic data of the sort which is captured in the human genome, and then there is proteomics data, there is reactomics data, all the way down to toxicopharmacogenomics data, and so on. So there are now many, many subdisciplines, all of which rest upon the kind of high-throughput experimentation which was responsible for decoding the human genome. But there is also a family of other kinds of data. There is image data, radiological data, MRI data, electronic health record data, insurance data, and so forth. And all of this data needs to be available in such a way, first of all, that you can find it. Secondly, so that you can compare it and combine it with other kinds of data that you have available. And then also in such a way that you can check it for consistency and reason with it in order to draw new conclusions. And we're really only at the beginning of understanding how we can address these kinds of problems. The exactly parallel kinds of problems arise, for instance, in the world of the U.S. Joint Forces Command Joint Architectures and Capability Engineering Division, where they have many different kinds of data about weapons, about services that need to be performed, about the human beings that they have available, about the activities that they engage in, such as training activities, the tasks which those activities involve, the subtasks which those tasks involve. All of these kinds of information are kept often in multiple different ways, in multiple different databases. And now the Army and the military forces, not just in the United States, but around the world, are trying to address the problem of how they can make these data interoperable, as the word used. Now, in the medical world, there is a very simple kind of problem, which again, we're only just beginning to learn how to understand and also learn about the difficulties of solving. And that's the problem of what happens to your data when you move from one hospital to another, or when you move from one doctor to another, or from one doctor to a hospital, or from one town to another town, or to another country. This is a problem which has a spatial aspect in the sense that you might move from one hospital to another on the different side of town. Problem being that the two hospitals use different database systems. They use different electronic health record systems, which use different terminology. But it also has a temporal aspect in the sense that you start off as a child, and then as you grow older, you get different kinds of diseases. You go to different kinds of hospitals. And as you move from one hospital to another, then somehow your data should go with you. And very often it doesn't go with you. And even if it does go with you, it's not necessarily the case that the hospital which gets the data can make sense of it. So this is a very interesting posting called "The Data Model That Nearly Killed Me," which is about how somebody who was actually an expert in these kinds of problems, an expert in health information technology, who had a asthma of a serious form. He arrived at a hospital with documentation about his asthma, but for different reasons, the hospital wouldn't use the documentation which he brought with him because it came from another source. So they wanted to check everything again. And that took a long time, I think 2 days, during which time his illness became worse and worse, to the point that he reckons that another hour and he would be dead. Now, in fact, a nurse in the second hospital took pity on him, and she read the data from the original hospital and found the cure and gave it to him, and he just needed a certain pill, which was described in the raw. Now, the problems which caused this particular situation are not just problems of the sort which ontology can help to address. There are also legal problems, economic problems, and so forth. But still, they are in part problems which this kind of ontological activity help resolve. Another interesting post has the title, "Are Health IT Designers, Testers, and Purchasers Trying to Kill People?" So this is a sample problem presentation page generated via auto-population in an electronic health record. What that means is that you have a hospital with an electronic health record, which is a good thing. And this particular electronic health record is based upon an artificial intelligence-based program which generates a problem list for this particular patient with a date associated with each problem. Now, a problem is basically something like an illness or a symptom or a concern which is relevant to the health situation of a given patient. Now, the first problem with this problem list is that it's hard to imagine that anybody could make sense of a long list like this. There are just too many items on the list. They're not formatted in a way which is useful to the person who might have to use the information which is here presented, particularly in an urgent context. But another problem is it contains an entry, atrial fibrillation. Atrial fibrillation is quite a serious matter. If you have that entry on your electronic health record, then doctors and nurses are going to treat you in a special way. Problem is that the atrial fibrillation which is on this list, a list which was generated by a computer, is there because a nurse needed to order a blood clotting test, and she entered the reason for the test as atrial fibrillation because she knew that that was a good way of getting the order fulfilled. If you write down something like atrial fibrillation, then they will get your order through quickly, and she needed to go home, I don't know. Now, in order to get this entry removed, if it's detected as being an entry which shouldn't be present on the problem list, you have to go back to the vendor, to the software company who built the electronic health record, to have them remove this thing deep in the back office where they keep the data. Now, all of these are problems with electronic health records which could indeed kill patients. Almost certainly have already killed patients. And they're problems which have to do with usability of the visual presentation of the information, usability when it comes to entering the information, because if it's hard to enter information, doctors won't use the system. But which have to do also with the ways in which information can get into the system. For instance, here, where information is there which shouldn't be there at all. Another problem is that this thing is alphabetical. Alphabetical is not a bad thing, it's just not clinically so relevant. A further problem is that there's lots of redundancy here. So we probably don't need 3 different kinds of diabetes to be listed. We may do, but probably we don't. There is historical information here about tests which were done alongside information about actual clinical problems. And again, it's probably not useful to list test information under the heading problem list. Now, this is bad enough, but when patients move around and this thing has to be exploited by another hospital system, which is programmed to expect quite different kinds of information, then you can imagine what happened. Various things happen, not all of them good. Now, one of the reasons why these things happen is because the electronic health record systems are, for obvious reasons, built by software engineers. Software engineers are not always clinically competent, and they are not always aware of the needs and stresses and strains of a hospital or a doctor's office. They are also faced with tremendously complicated software problems. And to create software which can work in one hospital is a very difficult business. It would be an even greater and more difficult business if one had to create software which would work in every hospital in a country like the United States, anyway, where hospitals buy their electronic health record systems on a commercial basis, because the vendors of electronic health record systems need to keep their intellectual property right in what they create in order to afford the incredible cost of the software development. So this is a very difficult, complex set of incentives which lead to very unsatisfactory outcomes as present system is constructed. Now, one subgroup of the reasons for those satisfactory outcomes is illustrated here. If I were wanting to design a patient record, then I would want the patient record to be a record of things which are true of me. For instance, that I really do suffer from atrial fibrillation. As we saw yesterday, there is a way of conceiving what goes on in the database world, according to which a database is not really about the object which it's designed to describe at all. Rather, it's about a world which is created by the database. We illustrated this issue by describing the way in which gender is treated in a database. And a database designer has to decide how to deal with gender. He has to decide how many genders will be included as options within the database. And if he only includes, let's say, 3 genders, male, female, and other, then there are only those 3 kinds of genders in the world as is described by the database. And if you are other, then you're neither male nor female, even if you are other, because for one reason or another, the nurse or whoever filled in the relevant document didn't know what your gender was. And what that means is that people end up being neither male nor female in a database because somebody who was filling in a form, for whatever reason, didn't have sufficient information. This means that the ontology of you in that database turns not on the way you are, but on a lack of knowledge on the part of somebody else at some point in the pipeline of gaining information. Now, that is not the kind of electronic health record which I would want to have describing my health state in a hospital. That kind of record arises because people are building records as if they were databases, which is quite reasonable because that's the expectations which software engineers bring to the problem of building a record system. And the term which is used to describe This aspect of electronic health record information is the term information model. The electronic health record from this perspective is not a record of the patient's health state, it's a record of information in a system, which, if we're lucky, is information about patient health. What I want is a patient-centered electronic health record rather than an information-centered electronic health record. And the issue is, how do we get this patient-centered electronic health record, given all the constraints and all the various incentives that I described earlier? Now, the most influential institution in the information model world of health or electronic health information is an organization called HL7. Stands for Health Level 7. Health Level 7 means the 7th level health information, where the very bottom level is the actual hardware. Then you move up to ever higher degrees of abstraction. Now, if I want an electronic health record, I want it to be about patients, our physical things. I want it to be about entities. And this is how HL7 defines an entity. An entity is a physical thing or a group or an organization capable of participating in act while in a role. And if we look at the HL7 reference information model, we see that physical things as so defined, entity, can have various states. It can have the state of being active, which means, and this is already rather a problem, active means the state representing active. And that sounds as if we have a dangerous circularity here, because if active means the state representing active, then active means the state representing active, and so on ad infinitum. But leave that aside. Or inactive, the state representing the fact that an entity can no longer be an active participant in the event. Or normal, is the typical state, which excludes nullified, which represents the termination state of an entity instance that was created in error. And then nullified, which is the state representing the termination of an entity instance that was created in error. So an entity is a physical thing, like me. I can die, thereby cease to exist. But I can also cease to exist by being terminated, because I was created in error. And what this means is that for the HL7 system, there are two ways of ceasing to exist. One is the normal way, where you die, and the other way is to be deleted from a database. That is called the error of use and mention, which we described already yesterday, confusing an object with data about an object, or confusing a word with the meaning of the word. So what does active and inactive mean as applied to person? Is there a special kind of death through nullification in the case of those instances of person who were created in error? Now, I don't believe that you can get a clear answer to such questions by looking at the HL7 documentation, because they are just not clear about the distinction between an entity and information representing an entity. Now, in response to these problems in HL7, and HL7 is an incredibly influential organization, I created this blog. It's the only blog I create. I'm not sure whether this is really a way to lead a healthy and fulfilled life. But I created this blog, which you're all welcome to go and inspect, which contains some interesting postings about the world of HL7. Now, the blog really was my attempt to try and understand what they were trying to do. And this is a summary. one small part of what I discovered when exploring the world of HL. But when HL7 says person, they don't really mean person. They mean objects in information systems which are created through processes of data, and it is a data instance. Person is not a person, it's a data instance. A disease is not a disease. It's, again, something like a data instance or the result of an observation or a record of an observation. So you suffer, from the HL7 perspective, suffer from diseases only indirectly in the sense that there is a data entry corresponding to you, which is associated with the data entry corresponding to the result of an observation of a disease. So you undergo, persons in this sense don't undergo processes such as being treated or falling ill or being born, which you would think are the health relevant processes of interest, but rather you undergo the data representing you, the person, undergoes processes of being revised, reactivated, nullified, and so on. Now, this kind of problem could be defended, has been defended by very intelligent practitioners of information modeling who say we need to represent the entities in reality inside the computer. You can't get orange juice inside a computer, so you have to put inside the computer some name or label and then treat that as if it was orange juice. And they're allowed to do that. So you shouldn't do this at home, but an information modeler is allowed to do that because he or she knows what they're doing. So we can feel safe that nothing will go wrong as a result of this process, which is the way you write software based on this information model approach. Another example is illustrated here. This is another influential piece of work. It's a guide to creating your first ontology, which was built by two leaders in the field of ontology development from Stanford at the time when this was written. So Ontology Development 101, namely Natasha Noy and Deborah McGinnis. It's about building a wine ontology. And it starts by pointing out that ontologies have become core components of many large applications, but we don't have training material to keep pace. And so this paper addresses the issues of why one would build an ontology and presents a methodology for creating ontologies based on declarative knowledge representation systems. Now, this declarative here, I think that means that we're going to create wine inside the computer. We create glasses of wine, bottles of wine, and so on inside the computer. Now, you can see what that means. And let's see what they say. So, an ontology, together with a set of individual instances of classes, constitutes a knowledge base. In reality, there is a fine line where the ontology ends and the knowledge base begins. I think I know exactly where knowledge of instances and ontology are divided. Ontology is about what is general. Knowledge of instances is about the instances of what is general. I think it's clear, and there's no issue about whether this piece of paper is an instance or a class. It's an instance. It's an instance, whatever you're interested in, whatever you're doing, whether you're a wine trader or a wine drinker or a wine chemist, it's still a piece of paper, an instance of the kind piece of paper. Classes, what is general, are the focus of most ontologies. That's all right, I suppose. But then we have classes describe concepts in the domain. I don't really know what that means, but for example, a class of wines represents all wine. Specific wines are instances of this class. The Bordeaux wine in the glass in front of you, assuming there's Bordeaux in the room, is an instance of the class of Bordeaux wine. But that Bordeaux wine in the glass in front of you is an instance of the class of Bordeaux wine. take a snapshot of that sentence, move along. Now, so we'll read it again. The Bordeaux wine in the glass in front of you is instant. Now let's look at the definition of an instance. An instance is a concrete occurrence of information about it. This is on the same page as the Bordeaux wine in the glass in front of you is an instance of Bordeaux wine. An instance is a concrete occurrence of information about a domain that is entered with knowledge. So the Bordeaux wine in the glass in front of you is entered into a knowledge. For example, Fran Smith might be an instance or a name slot. I think Fran Smith is the name of somebody called Fran Smith, who is a concrete occurrence of information about a domain that is entered into a knowledge. An instance is entered via a form generated by Protégé 2000. Now, there is a lot of use-mentioned confusion. Individual bottles of each wine may become individual instances in our knowledge base. This is the Protégé glossary. The Protégé is a very important ontology editor software system developed in Stanford, which both Deborah McGinnis and Natasha Noy, I believe, made important contributions. So we can create an individual instance Chateau Morgon Beaujolais to represent a specific type of Beaujolais wine. Chateau Morgon Beaujolais is an instance of the class Beaujolais. It's an occurrence in an information. And now they say that deciding whether a particular concept, and the example they have in mind is the Bourgogne region, is a class in an ontology or an individual instance, for instance, in France, if France exists, which we will discover later on it doesn't, depends on what the potential applications of the ontology are. So this is a piece of paper. I believe that this is a piece of paper, an instance of the class piece of paper, independently of what my intentions are about applying some ontology. The fact that I want to apply an ontology in one way or another does not make this into a class. It's always an instance. So individual instances are the most specific concept represented in a knowledge base. We're only going to talk about pairing wine with food. We'll not be interested in the specific physical bottles. The wine class is then a collection, not of individual bottles, but rather of the specific wines produced by specific wineries. The wine class in some ontologies is one thing, in some other ontologies is another thing, they said. In this way, of course, ontologies of wine multiply. And this is part of the methodology here. We need many ontologies because each ontology should be tailored to a specific use. We need many electronic health record systems because each health record system should be tailored to a specific hospital. Thereby, none of the electronic health record systems work well together. We can begin to see some of the reasons for this as located within the specific problem, information models. But if we want to maintain an inventory of wines in the restaurant, then individual bottles of wine may become individual instances in our knowledge base. Now, this Ontology 101 was published some years ago, I think in 2002. And it rests on an approach to ontology development, which is almost certainly no longer pursued. I hope not, at least. It's still maintained on the Stanford website as a Ontology 101 guide building ontologies. I have requested that they change it to take account of new advances in ontology. They didn't change it. I think my request was expressed in a a gentlemanly, polite fashion. But at this time, these authors believe that if concepts form a natural hierarchy, then we should represent them as classes. That is to say, wherever we have a hierarchy, then the entities which are structured as a hierarchy must be classes. That means they must be something general. That means they must not be instances. Consider the wine region. Initially, we may define main wine regions such as France, United States, Germany, and then more specific wine regions such as Bourgogne. Now here we have hierarchy. We have France, Bourgogne region, and the Côte d'Or region, which is a sub-region of the Bourgogne region. This is a hierarchy. And according to the rule that all hierarchical relations in the knowledge base are subclass relations, follows that all of these things are classes. France is a class. Now, the Bourgogne region is a class, which means that it has instances, maybe. But the class is something abstract. Bourgogne region, it's full of mud and wine and hills and road. It's not a class. It's something concrete and specific, which changes with time. It doesn't have members or instances. There is a mistake here. And the mistake comes from supposing that only classes can have instances and only classes can have subclasses, and that all hierarchical relations are subclass relations. We are ignoring here one very important kind of hierarchical relation, which is the part of relation. This is a simple mistake which comes when supposing that if you have a hierarchy, then you can build a class hierarchy. In fact, there are many hierarchies which have nothing to do with classes at all, and this is an example. Now, from this we can infer that the Alsace region does not exist. Only classes can be arranged in a hierarchy, they say. Knowledge representation systems do not have a notion of sub-instance. In fact, the Alsace region is a sub-instance. Part. France is an instance. The Alsace region is an instance. This is a part of this. This is a sub-instance. This. Knowledge representation systems, they say, do not have a notion of sub-instance. Therefore, if there is a natural hierarchy among terms, we should define these terms as classes, even though they may not have any instances of their own. Now, therefore, all of these things are classes. And if there are no instances, nothing here can be an instance. What could be an instance of the class Provence? It can't be Provence because that's a class. It can't be any subregion of the Provence because no subregion of the Provence would be an instance of Provence anyway. But subregion would have to be a class because it stands in a hierarchical relation to the superregion, which is Provence, and from there to the higher superregion, which is France. From this, we can conclude that the Provence and Alsace and so on. There are classes which are entries in databases, but there are no instances of these classes out there in the world. Now we can create in our database an individual instance Chateau Morgan Beaujolais to represent a specific type of Beaujolais wine. And then we say Chateau Morgan Beaujolais is an instance of the class Beaujolais. But how can you create such an instance? Well, just by making an entry in your database. And when you're making entries into databases, then you can assign things to instance or class more or less according to your choice, they say. But that's because they allow ontologies to be proliferated according to whatever choices the ontology requester wants the ontology builder to make. So if a given restaurant owner wants an ontology for this particular restaurant, then Noy and McGuinness will build one for them. If a group of wine merchants wants an ontology for their particular wine stores, warehouses, shipping depots, and so forth, then they will build an ontology for them, and they will build each one of these ontologies as a separate job. And the result, of course, is that much of the work that they do will have to be redone, and that the work that they do will not interoperate. It will be a collection of independent silos. So the result is that from this perspective, we can't say what the instances are. In some ontologies, wines are the instances, which means that they are entered in the instance boxes in the databases. In others, the bottles are the instances. In others, the vintage. Yes. And we've had this. This is from the Protégé glossary. I'm not sure if it's there now, but it certainly was there a couple of years ago. Individual bottles of each wine may become individual instances. That is to say, concrete occurrences of information in our knowledge base. I'll read that again 7 times. There's something wrong here. But of course, there's something wrong. And even if you know what you're doing, even if you're a very expert information modeler, there's still something wrong. Now, similarly, Microsoft Health Vault defines an allergic episode as an occurrence of an allergy which is defined by the allergy type symptom, are defined elsewhere within Microsoft knowledge. But then we are told that allergic episode inherits health record item, which means that everything which is true of health record item is also true of allergic episode. Health record item is higher in the hierarchy than allergic. A health record item is defined as a single piece of data in a health record that is accessible through the Health Vault service. What this implies is that every allergic episode is a single piece of data in a health record that is accessible through the Health Vault service. So all the allergic episodes in the entire history of all organisms, as far as I'm concerned, are already in the Health Vault system as single data items, which is a mistake. An allergic episode isn't a piece of data at all, and most of them are not accessible through Microsoft's Health Vault. Most of them never will be. And the same is true of exercise sessions, which are also described as health record items. An exercise session can be recorded, and the data may be entered into the Health Vault, but the exercise session itself is not data. I know that this is hard to believe, but most of the computational representation of the important things in our world, like allergic episodes, are done in this way. Pizza. There is something called the pizza ontology, which is often put forward as a good educational tool for teaching people how to build ontology. Exercise 22 is create an American hot pizza. An American hot pizza is almost the same as an American pizza, but has jalapeno peppers on it. Create this by cloning the class American pizza and adding an existential restriction along the has topping property with a filler of jalapeno pepper topping. So this is, again, the use mentioned. There's something wrong if you say swimming is healthy and has 8 letters, or 8 is the square root of 64 and is the output of a measuring device. What is the output of the measuring device is not 8, but 8. All right, now, how do they justify this? Well, the standard software engineering methodology places a huge emphasis on usefulness. And what they mean by usefulness is that they get to write software which runs, and then they can pass this software on to the customer, for instance. Now, it's much easier to write software if we have very simple models. And simple models are fine, because even if reality were non-simple, we could never know that, because we don't know what reality is like, because we only have our concepts of reality, and your concepts of reality are different from my. Now, one of the astonishing discoveries I made when I was still a philosopher, and when I started to talk to computer engineers, is that nearly all of them, probably without knowing it, are Kantian. They all believe that we cannot know what nearly all believe that we cannot know what reality is like. And they get upset if you suggest to them that maybe we should try and know what reality is like before we represent it in an information system. And you can try this experiment next time you talk to a software engineer. So one could summarize the argument for ontology as conceptual modeling or information modeling like this. Ontology, doing it right, is hard. Life is short. So let's not do ontology at all. Let's do conceptual modeling. Programming real ontology into computers is hard. Therefore, we will simplify ontology and not care about reality at all. So, painting the emperor's palace is hard. Therefore, we will not try to paint the palace at all. We will be satisfied instead with a grainy snapshot of some... Oh, I lost my other building. I had a really ugly building. Anyway, each information system ontology or conceptual model uses its own terminology and its own way of dividing up the domain of objects. And the result is there is no calibration there. And now, very quickly, an alternative approach. There are many ways to create ontologies, as the wine ontology case proves. The idea is that you do a good one first. You work out what goes on in the world of wines. There are regions, there are bottles, there are glasses, there are chemicals. And you do an ontology of all of those things. One ontology which you do really well by collaborating and consulting with the experts who know about chemistry and enology and so forth. And then when you have a specific customer who needs an ontology of wine bottles or whatever it might be, you just take the relevant parts of what you need and add a user interface which will enable the customer to get what he needs. In this way, you avoid redundancy. You have something which can be grown and contributed to over time by multiple different groups of experts who will be concerned to maintain the utility and the consistency of the ontology because they get benefits from its being maintained. Right? And but you make less money because you can't sell new ontologies all the time, and neither can your colleagues, other computer scientists. And so the incentive is to not do it this way, but rather to do it in the way which creates multiple new ontologies. So, but now we can understand what we might think of as science-based ontology development. How are you to create ontologies in such a way as to avoid the creation of silos? The answer is that you take reality as your constraint. And the way you do that is to look at the best science that you have available at any given time. And in many domains, that best science will be relatively stable. And you probably should not be building ontologies in those domains where science is still unsettled in any case. Wait until we have established scientific textbooks. So the fundamental principle of ontological realism is find out what the world is like by doing science, and then build your ontologies in such a way that they're adequate to this world rather than to some simplified model. Now, this is already working. So in the world of biology, particularly this approach to ontology, whereby ontologies are created carefully by experts in such a way that they interoperate, is already showing very considerable successes. And to this degree, the ontology activity which is taking place in biology is part of science. It's not part of philosophy. It's not part of information modeling. It's not part of computing. Part of scientific activity of biology itself. And as it happens, the ontologies which are being built as parts of science have to be associated with various kinds of software tools. This is true of other parts of science. Large gene array can only work in association with complex software. That doesn't mean that gene array investigations are part of computer science. It just means that software and computers have become a necessary part of so many activities in the world today. So the ontologies themselves are not engineering artifacts, even though we need software tools to make them work. And in fact, the same ontology can be associated with typically multiple engineering artifacts. So ontologies like the gene ontology are comparable to scientific theories or to scientific databases or to scientific journal publications. They are not computer engineering artifacts. They are scientific artifacts. And as we saw already yesterday, these ontologies are being used by scientific journal publications in order to increase accessibility of scientific information. And in the Go world, we are carrying out experiments trying to introduce ontology peer review, which will be analogous to peer review, which is applied to scientific journals. And I will skip this, and I'll go to the goals, and then we will conclude with the discussion. So when you're building an ontology in science, you need specialists. And this is to repeat the results of our discussions yesterday. This work is difficult. It's not comparable to the traditional sorts of scientific work. It is in some ways comparable to the work of computer scientists. In some ways it's comparable to the work of philosophers. But it's a new kind of work. And in order to make this work possible, we need to work out what the principles are for doing it well. I think that we already understand from the basic axiom that silos are a bad thing in, for instance, a domain like healthcare, almost certainly too in a domain like wine. Silos are a bad thing. This means we need to create ontologies which do not generate silos, which means we need to create ontologies which work together so that the data which they are used to annotate should be capable of being integrated in a seamless way. But what principles will allow such ontologies to be built? This is a scientific question. And the way we will solve this question is by trying out different principles and seeing which ones do indeed give the best results. And we're doing that already. We are quite far along, We need to train a community of ontology experts who will be able to apply these, help test. And thereby, we will reach a point, I predict, where we establish ontology development as being a recognized, necessary part of the scientific enterprise in all of those areas of science where information-based research is important, which means practically all areas. Right? All right, so we'll stop there for this lecture and have some discussion. So people with questions should stand up.
Back to your discussion on healthcare and healthcare information systems. How much responsibility do you see each individual patient in flesh and blood world taking over their data in?
So I am, as is probably clear by now, a visionary zealot or a crazy man. So I hope not. So I think that patients should get to see all of their data because that helps to correct errors in the data. But also I think that patients should be willing to allow other people to see their data under different kinds of circumstances. But we should encourage patients to see that opening up their data, for instance, for research purposes, is a good thing to do. Just as giving blood is a good thing. So we should have cards in our pocket, which will say, when we die, which will say not merely you can have all my organs, but also you can have all my data.
Then the follow-up to that question is, whose responsibility, or is it an ontologist's responsibility to educate the general public on how to do that, how to interact with?
Yeah, I think that the ontologist has a proximate responsibility to educate scientific colleagues with whom he's working, build ontologies, that open source accessibility of data is a good thing. That's the first circle. There are further circles which spread then out towards patients. And I'm doing a small part of that kind of work with my HL7 blog. One of the problems with HL7, I believe, is that it's very difficult to understand what HL7 is because the documentation is so poor. And to improve documentation would mean improving the system as well, making it more accessible to more people, and thereby making it better. I think that Sunshine is the best. I don't want to sound cliches. No what?
We're talking about there is a relationship. Doesn't sub.
Yeah.
Except for it.
Yes.
There will be a part.
Yeah. So there will be both is a and part of in any good ontology.
So do you think subclass can both have the relationship with the class also for?
Give me a concrete example of what you have in mind.
I don't know if
you mean whether there can be part of relation.
One class also a sub.
But okay, so I'll give you an example of what I think you have in mind. I think probably the answer to your question is no, but let me give you a concrete example just to make sure I've understood it. So in anatomy, we have part is a subclass of organ. And we have part is a part of organism. And we have organ is a part of organism. So we have part, subclass, organ, part of organism.
Then make the
Yes. The reasoning, it becomes more complicated if you have part of. But now you're thinking like a computer scientist. So there are some people who try to build anatomies without using more than one relation. The standard relation that they choose is, in fact, part of. So I believe that the Edinburgh Mouse Anatomy Atlas, which is one of the most significant contributions we have to anatomical ontology, uses only part of. It doesn't have any subclass relation. But I believe that the FMA, the foundational model of anatomy, which is human anatomy, which has both ISA and part of, and some other relation, is a much better representation of anatomy than the mouse representation, precisely because it has a richer repertoire of relations. And that makes reasoning difficult. And if you have a reasoning need where the difference between is and part of is unimportant, you can just collapse two. For your own particular need, the FMA and the mouse anatomy ontology are both publicly available, and you can use them in any way you like. So you shouldn't try to impose simplicity on the ontology in order to satisfy a particular engineering need, because then that ontology becomes less useful for other people who have different engineering needs or other needs which have nothing to do with engineering.
To make the same comment, a lot of this simplification arises simply from the fact that the software is not able yet with the proper relationship.
Yeah.
Prodigy is a key example. All these gyrations you showed about Prodigy definitions, they all have the basis in Prodigy not being able
Yes.
to represent the relationships that it used to represent. So they cannot understand that strand, no class at all. Actually, an instance.
But I think that Protégé now, while the documentation of the terminology is still not as good as I would like, does, at least with the OWL plugin, have the ability to represent relations with the same degree of sophistication as OWL DL. Now, that is not a very high degree of, but still, it is more than just ISA or subtype. It includes also any relation in OWL. And I believe that Protégé will, at some stage, incorporate a first-order logic or a common logic plugin, which we'll talk a little bit about in a later lecture. Yes.
Yeah, we'd want to critique your deconstruction of the sort of the wine tree with the regions.
Yeah.
In this case, I don't think they're referring to regions in France, but a type of wine has the property from this region in France. I wouldn't go into a liquor store and say, I want a Chateau Cousteau wine. I'd say I'd want Uncle Jack's wine, which happens to be of the type Chateau Cousteau, which is a specific problem and sort of the ambiguity of their ontology, but not say that sort of just their labeling.
Yes, so that part of the problem, I think, is that when they wrote the Ontology 101, they were writing for beginners. And so they thought it would help beginners to make these things more concrete. So they say, oh, an instance, that's the glass of wine in front of you on the table. People understand what that means. Problem was that in making this effort, make this rather abstruse stuff accessible to beginners, they was false advertising. An instance is not the glass of wine on the table in front of you. It's something which is inside a database. So the result is actually less helpful to a beginner than it would otherwise be. Now you are, I think, stating something which would have helped them to do a better job of what they were doing by distinguishing region in France from collection of all of those wines which are of that regional character and were grown in that region. That would have made it less accessible to the beginner. So they just talk about the Bourgogne region. They don't talk about wines grown and cultivated in the Bourgogne. So if they had been writing for people with more expertise, then they could have been more precise in that way. Then they would have defeated the object of an introduction. So what I think they should do, given that technology and understanding has grown in the last 7 years, is to rewrite the thing, make it still for beginners, but eliminating those errors which are problematic. And I'm still hoping that they make. More questions? So let's break for coffee, and then we'll meet again in 15 minutes.